Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, in this session today we would be talking on a very new topic. The topic is pyrrole, a heterocyclic compound, and for this very discussion we have with us in our studios Dr. Sushila Singhal. Dr. Sushila Singhal is Assistant Professor in Department of Chemistry, Deshbandhu College, University of Delhi. So let's welcome Dr. Sushila Singhal and let's try to understand what pyrrole is. Hello ma'am, welcome to the UGC lecture.
Thank you Geetika ji. Today's lecture is on pyrrole. Pyrrole is a 5-member heterocyclic compound. First of all, I want to say that why these heterocyclic compounds are very important. These are very important compounds in the organic synthesis because these compounds are present in many natural products. I have divided my lecture into the two modules, the module 1 and the 2. The module in module 1 will discuss the pyrrole introduction. Then how pyrrole is isolated from the natural sources, how the pyrrole structure has been designed, then the aromatic character of the pyrrole, preparation of pyrrole, and preparation of the substituted pyrroles which have many importance in the organic synthesis. These preparation of substituted pyrrole contains 3 named reactions: Pal node synthesis, and Hens synthesis. Then we will discuss the pyrrole derivatives, in which we will discuss the derivative which are due to the reactions of the pyrroles, and then the applications of pyrrole in the natural products. In the module 2, we will discuss the many properties of pyrrole. Properties of pyrrole has been divided into 2, physical and chemical properties. In the physical properties, we will discuss about its dipole moment, its solubility, etc. And in the chemical properties of pyrrole, we will consider basic character of pyrrole, acidic character of pyrrole, and many electrophilic substitution reactions. Since this is an aromatic compound, it shows electrophilic substitution reaction, which will include halogenation, nitration and sulfonation, Friedel-Crafts acetylation, and formulation. Formulation is the reaction in which we can increase the number of carbon atom, which can be shown by 2 named reactions. One of them is Getterman-Koch reaction and the another one is Riemer-Tiemer reaction. Then we will do the reactions of reduction of pyrrole and oxidation of pyrrole. Pyrrole also shows many other reactions like Mannich reaction with malic anhydride, Hofmann's exhaustive methylation, which is a very important reaction in case of alkaloid preparations. Pyrrole also undergoes ring opening reactions and condensation with the aldehydes. Then we will summarize the today's lecture, and then there will be few questions for the exercise. Now the module 1. In the module 1, we are discussing the pyrrole, a heterocyclic aromatic compound. First of all, we should understand that what is a heterocyclic compound. All organic compounds contains mainly carbon and hydrogen as the main element. If any other element other than carbon and hydrogen like nitrogen, sulfur and oxygen is present in the organic compound, then the organic compound will be hetero compound. Now since this pyrrole is a cyclic compound, so this pyrrole is a heterocyclic aromatic compound. Since we are saying here that it is also an aromatic compound, so we should also understand that what is this aromatic. Aromaticity means, aromaticity is a term which is derived from the word aroma. What is aroma? Aroma is a word which means fragrance smell, and this fragrance smell is present in many of the natural products. So the compounds which are having the fragrance smell are aromatic in nature, but this is the physical property as it is a smell. So there are many more criteria for the aromaticity of the compound, which we can see from the structure and from the chemical properties. In this slide, we have shown the ball stick model of the pyrrole, where this blue color ball is of nitrogen and hydrogen is associated with this. The grey balls are of the carbon compound and these white balls are of hydrogens. The molecular formula of pyrrole is C4H5N. Pyrrole is a 5-membered aromatic compound. There are many other heterocyclic compounds are also there, in which we are having 6-membered, 7-member aromatic heterocyclic compound. This is a good example of 6 pi electron aromatic compound bearing one heteroatom. Here we are having the 2 double bonds, so 4 pi electrons are there by these 2 double bonds, and 1 lone pair is present on the nitrogen atom. It is a colorless volatile liquid that darkens readily upon exposure to air, so it is very reactive on exposure to oxygen. It is sparingly soluble in water but readily soluble in alcohol and ether. It gives red color on pine splint moistened with hydrochloric acid. So it shows brown color also, sometimes it shows red color. It is reactive with the oxygen atom. This pyrrole is firstly isolated from the bone oil, which is called as the pyrrolysate oil of the bone. Pyrrole nucleus is a part of cofactors in the enzyme studies and in many natural products like alkaloids, vitamins, etc. It is important among all other heterocyclic compounds like indole, quinoline, isoquinoline and others. Why? Because its nucleus occurs in various natural products. For example, in case of chlorophyll. Chlorophyll is a green pigment present in the leaves. The green color of the leaves is only because of this chlorophyll, and this chlorophyll contains the pyrrole units in its main structure. Then comes the hemine. Hemine is the blood pigment. The red color of the blood is only because of this hemine, which also contains the pyrrole nucleus in its main head. Then comes the bile juice, which is secreted from the liver. This bile juice contains 2 pigments, one of them is bilirubin and one of them is biliverdin. This bilirubin also contains the pyrrole nucleus in them in porphyrin rings. And many other alkaloids and B12 also contain the pyrrole nucleus. Now, how this pyrrole is isolated from the natural sources? Pyrrole occurs in coal tar and the bone oil, that is the pyroxylate oil. Generally, this is isolated from the bone oil obtained by the pyrolysis of the bone. It is a commercial isolation of the pyrrole from the bone. First of all, we take the bone oil in a big container, then we will extract it. We will get it free from acidic and basic substances by excessive washing with the dilute alkali and the acids. Then this extract, which is free from these impurities of acidic and basic substances, will then undergo fractional distillation, from where we will get the impure pyrrole. Still it is impure pyrrole. Then it is needed to react it with the potassium hydroxide. Then we will fuse it with the potassium hydroxide to make it potassiopyrrole, which will then undergo steam distillation and we will get the pure pyrrole. This steam distillation is done because its boiling point will come at this below this water. So then here we will get the pure pyrrole. Now comes the structure of pyrrole. Pyrrole's molecular formula is C4H5N. As you can see from the structure, pyrrole structure, we are having the 2 double bond. It resembles like diene-like structure, and you also must be knowing that all diene, conjugated dienes shows addition reactions, but this pyrrole do not shows these addition reactions. It means it resembles like diene-like structure, but something more is there in this structure that can be explained on the basis of its resonance energy and on the basis of its orbital molecular structure. In case of conjugated diene, we have resonance energy only 12.5 kJ per mole, while in case of pyrrole we are having the resonance energy is about 100 kJ per mole. These facts ruled out that pyrrole is having a diene-like structure. This can be explained on the basis of the aromatic character of the pyrrole. Here we have shown the orbital structure of pyrrole. This is the aromatic character of pyrrole, can be explained on this orbital structure. All the 4 carbon atoms in the pyrrole and the nitrogen atom, both are sp2 hybridized. The hybridized orbitals of carbon and nitrogen are involved in the axial overlap, forming the sigma bonds, and these sigma bonds then will form the bond with the hydrogen atom. Each unhybridized orbital of carbon atom has 1 electron, while nitrogen atom has a pair of electron. So the sideways overlapping of the unhybridized orbitals will result in a delocalized pi electron cloud, which will account for the aromatic character of the pyrrole. Since we are saying here that pyrrole is aromatic in nature, so we should also know about the aromaticity of an organic compound. For an organic compound to be aromatic, there are 3 criteria. One of them, that it should have a cyclic structure, which we can see in the pyrrole. It should have a planar structure. Planar means it should have the pi electron cloud above and below the plane, which we can see in the pyrrole. It should have delocalized pi electrons, which we can show from the resonance structures of this. And aromaticity criteria, main aromaticity criteria is that it should obey the Huckel's rule. Now what is the Huckel's rule? Huckel's rule is 4n plus 2 pi electron, that the organic compound should have 4n plus 2 pi electrons, and the n is the number of an integer. Here we can see that there are 6 pi electrons, so 4n plus 2 pi electrons will be equal to 6, and here by calculating you will get the n number will be 1, that is an integer. So this pyrrole obeys the Huckel's rule, and we can say that this pyrrole is a aromatic compound. Pyrrole is a resonance hybrid of the following structures. Here there are 5 canonical structures, or you can say resonating structures of pyrrole molecule, in which we can see in the first structure there is a electron pair on the nitrogen atom, which will shift to the nitrogen and carbon 1, and then positive charge will come on the nitrogen. Then in the second structure, the electron pair will further shift or will further move to the C3 position. Then we will get the bond line in the position C3 and C4. Then this bond will again shift to the position C5 and nitrogen, and in the last one we will be having the electron pair on the position number C4. So we can see here that there is a positive charge on the nitrogen atom, and there is a electron pair shift on the carbon number 2, 3, 4 and 5 in the resonating structures of the pyrrole. So because of this delocalization of charges, because of this charge separation, there is a stability in the molecule. Pyrrole is a resonance stabilized structure. Then comes the preparation of pyrrole. Now this important compound pyrrole, how it can be synthesized? It can be synthesized by many ways. One of them is by passing the acetylene and ammonia through a red hot tube. Here we have taken the 2 molecules of acetylene, or you can say ethylene. When it will react with ammonia molecule in a red hot tube, fusion will be there and it will cyclize to give a pyrrole molecule. It is the simple pyrrole molecule. Next preparation method is by passing a mixture of furan, ammonia and steam over hot alumina. Here we have taken one more heterocyclic compound in which oxygen atom is a heteroatom in case of furan. This is a commercial preparation in which we can prepare the pyrrole molecule from the furan. Furan will react with ammonia in the presence of hot alumina at temperature 480 to 490 degrees centigrade. We will get here the pyrrole molecule, and only water will be the side product. So, this is the best method of preparation, that is why it is commercialized. Since side products are only water, it is a green method. Next synthetic method is by distilling ammonium musate and glycerol at 200 degrees centigrade. This ammonium musate first will decompose into the mucic acid and the ammonia. Mucic acid you can see in the reaction I have shown here. The former then will undergo dehydration, decarboxylation and cyclization by reaction with ammonia. Here you can see in the reaction I have marked with the dotted rectangles 3 molecules of water from the mucic acid and the 1 from the oxygen of the mucic acid, and the ammonia's 2 hydrogens will dehydrate to give the 4 molecules of water, and the 2 carboxylic acid group will undergo decarboxylation to give the pyrrole nucleus. We can also prepare pyrrole by the distillation of succinimide over zinc dust. This succinimide is a amide which is formed from the succinic acid. Succinic acid is a 4 carbon dicarboxylic acid which on reaction with ammonia give us the succinimide. This succinimide first will undergo enolization to convert its carbonyl carbons into the enolic form. Here you can see in the second structure there is an enol structure where we are having ene, that is the diene and alcoholic group together. So, it is a keto-enol tautomerism. Succinimide first undergoes keto-enol tautomerism to give the second structure, which will further undergo zinc reduction, will be reduced by the zinc metal and will give us the pyrrole nucleus. So, these 4 were the synthesis in which we can get the pyrrole nucleus in general. Now, in the organic compound synthesis, in the organic reaction mechanism synthesis, there is importance of substituted pyrroles also. So, for the substituted pyrroles, we have few named reactions. Few of the scientists, Pal and Noor, they have synthesized substituted pyrroles by condensation reactions. First of all, we are taking here the Pal-Noor synthesis, in which we will take the 1,4-dicarbonyl compound. First structure is 1,4-dicarbonyl compound, which will condense with the ammonia molecule. Ammonia will react on the carbonyl carbon and will start cyclizing the carbonyl compound. Then after the deprotonation and further protonation followed by hydrolysis will give us the 2,4-dialkyl pyrrole. By substituting this R and R dash in the structure number 1, we can get many substituted pyrroles. If we take these, the methyl, both are methyl groups, then we will get 2,4-dimethyl pyrrole. We can take them different also, like R methyl and R dash ethyl, then we will get 2-methyl 4-ethyl pyrrole. When 1,4-dicarbonyl compound is succinyaldehyde, that is R and R dash R H. Here these are not alkyl groups, these are hydrogens. Then pyrrole itself is obtained. You can see in the reaction in the first structure we have taken these R groups as the hydrogen. R groups has been substituted by the hydrogen atom. Then again ammonia will attack on the carbonyl carbon and we will get the second structure, which after deprotonation followed by protonation and followed by hydrolysis we will get here the pyrrole itself. Then comes the Noor synthesis. Noor scientist also synthesized pyrrole, substituted pyrrole, by the condensation of alpha amino ketone or alpha amino beta-keto ester with another ketone. Another ketone should have active methylene carbon. Now what is active methylene carbon? Active methylene carbon is a carbon in which we are having the hydrogens which can be easily donated, which can be easily lived out, which is active, which can be substituted actively, so they are called active methylene compound. Here we have taken ethyl acetoacetate as active methylene compound and alpha amino ketone. This is the alpha amino acetone we have taken. Both will condense together and small molecules, small water molecules will be leaved out to cyclize the molecule, which will enolize to give us the substituted pyrrole. One more synthetic method is there, that is the Hen's synthesis. This method involves the condensation of a beta keto ester and alpha chloroketone. Here we have taken alpha chloroacetone and ethyl acetoacetate. Here also ethyl acetoacetate is a active methylene compound which undergoes condensation very easily, and we have taken ammonia here. In case of ammonia we can take primary amine also. If we will take the primary amine, then we will have the substitution at the nitrogen atom also. So from here alpha chloroacetone on condensation with ammonia and ethyl acetoacetate, we will get here the substituted pyrrole. It is 2,5-dimethyl pyrrole ethyl acetate. These were the synthetic methods of the pyrrole and the substituted pyrrole. Now these pyrroles also form some derivatives. Pyrroles and its hydrogenated compounds pyrrolidine are found to be fundamental nucleus of various important natural products. For example, pyrrole nucleus is present in many natural forms in the chlorophyll pigment, in the hemine pigment, in the bilirubin and phyllocyanin pigments. Phyllocyanins are the synthetic dye stuffs which are formed in the laboratory, in the vitamin B12 also. All of these above natural products, natural pigments have pore firing rings in which we are having the pyrrole nucleus. These pore firing rings are the rings where we are having this pyrrole nucleus in a number of 4. 4 number of pyrrole rings are joined together to give a pore firing ring. Pyrrole on hydrogenation, or you can say on reduction, will give us the pyrrolidine molecule. It is a derivative of pyrrole where both of the double bonds have been reduced, have been hydrogenated. So now it is a cyclic molecule. This pyrrole is basic in nature. This pyrrolidine has the property of a secondary aliphatic amine. You can see in the cyclic structure of pyrrolidine that nitrogen is attached with the 2 carbons, so it is a secondary amine. It behaves like a secondary aliphatic amines. It has normal basicity of an aliphatic amines. Actually, pyrrolidine is 100 billion more basic than pyrrole. This is because of the fact that extra pair of electron on nitrogen in pyrrolidine is now exclusively available for protonation. How? In case of pyrrole, we are having the electron pair on nitrogen which is available for the aromaticity of the compound, which is used in the completing the sextet of the molecule. But in case of pyrrolidine, there is no sextet, so its electron pair are free for donation. As it is free for donation, so that's why it is basic in nature. Pyrrolidine is used as a secondary amines for making enamines organic compounds. This pyrrolidine nucleus, this pyrrolidine derivative is also present in 2 essential amino acids. Now the term essential amino acid, from where it is derived? Amino acids are the natural products in which we are having the amine group and the carboxylic acid group in the same compound, and it is a monomer of proteins. Now what is the essential means? Essential and non-essential, 2 type of amino acids are there. Essential amino acids are the amino acids which cannot be synthesized inside the human body. The amino acids which we will get from the food, which we will get from the extra sources, are called the essential amino acids. Two of the essential amino acid, one of the proline and one is hydroxyproline. You can see the structures in both of these amino acids. We are having the pyrrolidine nucleus in them. Also, few alkaloids like hygrine and nicotine, we have shown the structures of hygrine alkaloid and nicotine alkaloid also. Here also you can see the pyrrolidine nucleus in these two alkaloids. Now these two important pyrrole and pyrrolidine nucleus, how they are applicated to the general chemistry. These pyrrole and its derivatives are widely used as an intermediate in the synthesis of many pharmaceuticals, in the drugs and the medicines, in many agrochemicals, fertilizers, in dyes, in the photographic chemicals, in many perfumeries and other organic compounds. They are also used as catalyst for polymerization processes. These are very highly active compounds. These pyrrole and pyrrolidine are very active in nature. So, in the acidic condition, in the strong acidic condition, they undergoes polymerization processes. They are also used as the corrosion inhibitors, also used in many preservatives of many natural things, and as a solvent for resin and terpenes preparations. They are also used as the standard of chromatographic analysis. They are also used in many other organic synthesis. So, here in the module 1 we have discussed that how this pyrrole is important, what is the structure of pyrrole, what is the aromaticity of pyrrole, how this pyrrole can be synthesized, the simple pyrroles and the substituted pyrroles which we can synthesize from many important organic reactions. Thanks. So, in the module 1 we have discussed the preparations of pyrrole, and in the module 2 we will discuss the properties of pyrrole. Pyrrole shows many chemical properties and physical properties also. As pyrrole readily reacts with air, as we have discussed earlier also, so it is very important to purify all the time before it is used. So, it is purified by the distillation processes. Since it is having a electronegative atom nitrogen which creates a dipole in the pyrrole molecule, so it has a dipole in which positive end lies towards nitrogen with a dipole moment of 1.58 dpi. It is weakly basic with a conjugate acid value of pKa minus 3.8. It is also weakly acidic in nature at the nitrogen hydrogen position with a pKa of 17.5. These were the physical properties. Now comes the chemical property of the pyrrole, which first of them is basic character of the pyrrole. Now, what is a base? Base is a species where we can easily donate the electron pair. So, in case of nitrogen, in case of the pyrrole, we are having the lone pair on the nitrogen which can be easily donated. So, it is basic in nature, but it is weak base. Why it is weak base? Because it is aromatic compound, and we have discussed that this nitrogen electron pair, the lone pair present on the nitrogen, is available for the completing the sextet of the cycle. It is used for making the cyclic delocalization of electrons. Since these electron pairs are not readily available for protonation, hence pyrrole will behave as a weak base, It is much weaker base than pyridine. Pyridine is the higher analog of pyrrole molecule, which is a 6-membered heterocyclic compound bearing the nitrogen atom as a heteroatom. In case of pyridine, we are having 2 lone pairs on the nitrogen, and these 2 lone pairs are not involved in the completing the sextet of the hetero compound. So, one of the electron pair in pyridine, in case of pyridine, is available for donation easily, which is not in the case of pyrrole molecule. So, it is much weaker base than pyridine. Moreover, if a proton is added on the nitrogen atom by reaction with an acid, the species formed will be the pyrrolium cation. This pyrrolium cation is a very unstable species. Why it is unstable? Because there is no stabilizing factor such as resonance. You can see in the structure that there is a positive charge on the nitrogen, so there is no any option, no any preference for the resonating structures. So, it is less stable, it is having the high energy. That is why after this protonation, it is not available for making the salt. Then comes the acidic character. Now, what is an acid? Acid is a species where we can easily leave the hydrogen atom. Pyrrole is a weak acid due to the presence of immunohydrogen atom. There is a hydrogen on the nitrogen attached hydrogen that can be easily donated, but it is a weak acid, we are saying. So, what are the reasons for its less acidity? It can be explained on the following 2 facts. Due to the greater S character of nitrogen-hydrogen bond in pyrrole, the bonding electron of the bond, this NH bond, they are held more strongly to the pyrrole nitrogen because it is a more electronegative atom, and hence hydrogen is eliminated as a proton. Now, after the elimination of the proton, we will get an anion that is called the pyrrole anion. Once it is formed, it is stabilized due to resonance. In the first structure, we have shown this pyrrole nucleus. This is the pyrrole compound, which by the removal of this immunohydrogen will give us the pyrrole anion. This pyrrole anion is more stable than this pyrrole itself. You can see here that there are these resonating structure, these canonical structure of the pyrrole anion, which are resonance stabilized. Here there are 5 resonating structures in which this nitrogen containing the lone pair, this electron pair, this lone pair will be delocalized on the carbon number 2, the carbon number 4, carbon number 5 and carbon number 3. It means it is delocalizing over all 4 carbon atoms. But there is no charge separation in the pyrrole anion, there is no positive charge. So, the stability of this hybrid of this anion is even more than that of pyrrole. In case of pyrrole, we were having the positive charge on the nitrogen atom. That is why, therefore, pyrrole changes to anion by losing proton, and this accounts for its acidic nature. Pyrrole is not a strong acid, although it is many powers of 10 stronger than ammonia as an acid. Ammonia is a base, everyone knows that ammonia is a base, but this pyrrole is acidic than ammonia, although it is basic also, but it is sometimes it is acidic also. In fact, under vigorous conditions, pyrrole forms a salt with potassium hydroxide and Grignard reagents. Potassium hydroxide is a base. When it will react with the base, it will behave as an acid. It will form the salt with the base. Here you can see that it will react with the potassium to form the pyrrole potassium. And when pyrrole will react with RMgX is the Grignard reagent. It will form the pyrrole magnesium bromide, which is again a salt, and we will get here the alkane molecule also. So, in both of these reaction where it is reacted with the base, pyrrole here acts as an acid. Since pyrrole is aromatic, as we have discussed earlier also, that's why it will not undergo addition reaction, it will undergo electrophilic substitution reaction. Electrophilic substitution reactions are the reactions in which electrophile will substitute any hydrogen present on the organic compound. So, electrophile will attack on the pyrrole molecule and will substitute the hydrogens present on the carbon and will undergo many reactions. Pyrrole is very reactive towards electrophiles. Because of their pi electron density at the carbon atom of the pyrrole ring is high due to resonance. We have seen the resonating structures of pyrrole in which we were having the negative charge on the carbon atom, that's why they were having the high pi electron density at the carbons. Now comes the preference of the electrophilic substitution, that this electrophilic substitution in case of pyrrole will occur at which position? Will occur at position number 2 or 5 or 3 or 4. These 2 and 5 positions can also be called as alpha position, and position number 3 and 4 can also be called as beta position. So, the predominance of 2 substituted product over 3 position is because of the fact that the positive charge in case of position number 2, the transition state formed, the resonating structures formed will be more in case of attack at the position number 2 as compared to the position number 3 attack. In position number 2, we will get the 3 structures, 3 resonating structures, while in case of position number 3, we will get only 2 resonating structures, only 2 intermediate will be formed. More the number of structures, lesser will be the energy of the compound of the resonating structures, lesser will be the energy, more will the stability of the attack. So, on the basis of this less energy, more stability concept, the substitution will take place at the position number 2. Here we have shown the attack on the position number 2, this is the C2. This E positive is an electrophile, this electrophile will attack at position number 2. The bond pair will shift at position number 2, an electron density on the position number carbon number 2 will increase, yielding the electron deficient position 3. Then this electron deficient position will be delocalized by this electron pair and it will come at the position number 5. Then it will again come on the nitrogen atom. Nitrogen atom is having already the lone pair which can be shifted to make the nitrogen hydrogen bond pair. So, in case of attack at 2 position, we will get these 3 structures, and then after deprotonation of this hydrogen, we will get here the substituted pyrrole. Now, we will see the attack at position number 2. We have seen the position number 2, here we will show the position number 3 attack. This electrophile will attack on the position number 3. This bond pair will shift here, making the electron density high on the position number carbon number 3. Then there will be the 2 resonating structures formed. As we have seen that in attack at position number 2, there we were having 3 resonating structures and here only 2 structures are there. So, the attack at position number 2 will be preferred. This was the preference of the electrophilic substitution. Now, there are many electrophilic reactions. One of them is halogenation. Since pyrrole is highly reactive, halogenation takes place very vigorously and will require careful control of reaction conditions. In case of halogenation, it will undergo chlorination, bromination, iodination. Chlorination will be carried out with sulfuryl chloride in the presence of ether, and we will get here the 2, 3, 4, 5 tetrachloropyrrole. When this pyrrole will undergo bromination, it will take place in the presence of aqueous ethanol and we will get here 2, 3, 4, 5 tetrabromopyrrole. Iodination of pyrrole will be carried out in the presence of iodine and aqueous potassium iodide, and we will get here 2, 3, 4, 5 tetraiodopyrrole. We have discussed that substitution will take place at the position number 2 and 5 preferably, but if these 2 and 5 positions are already blocked, already substituted, then the further substitution will take place at the position number 3 and 4. Here in case of all halogenation reactions, we will get the tetrahalogenated product. This iodination product 2, 3, 4, 5 tetraiodopyrrole, this possesses many antiseptic properties and is used in medicine under the name iodole. Nitration and sulfonation are also very important electrophilic reactions. Since strongly acidic condition causes polymerization of this highly reactive pyrrole, so special mild reagents, weak reagents are used for nitration and sulfonation. For nitration we will use the acetyl nitrate, and for sulfonation we will use the sulfur trioxide pyridine complex. Here in the reaction we have shown both reactions together. Here this is the left side is the nitration reaction where we will get 2 nitropyrrole product, and in sulfonation we will get sulfonation at the position number 2 and we will get the pyrrole 2 sulfonic acid. We have also shown the mechanism of nitration. Mechanism of nitration is similar to that of electrophilic substitution in aromatic compounds, that is of benzene, the simplest compound. The steps are similar. The first step is the generation of the electrophile, since electrophile is required for the attack. We are using here the mild reagent, that is acetic anhydride. It will react with nitric acid to give us the acetyl nitrate nitonium ion. Acetyl nitrate is a electrophile here. In the second step, this nitonium ion will attack on the pyrrole ring at the position number 2. Here is the attack at the position number 2. Then we will get these 3 resonating structure, and this is the resonating hybrid of the attack on pyrrole ring at position number 2. Then the third step of the substitution is the elimination of the proton present at the position number 2 to give us the 2 nitropyrrole. This is the acetate ion which we will get from the acetic anhydride. This will again accept a proton to make the acetic acid. Similar sequences can be written for sulfonation also and for other electrophilic substitution reactions also. Then the next electrophilic reaction is the Friedel-Crafts acetylation. Pyrrole undergoes acetylation with the help of acetic anhydride at 250 degree centigrade temperature to give the 2-acetyl pyrrole. Here also the substitution will take place at the 2-acetyl pyrrole position, will the position number 2. Next reaction is the formulation reaction. Formulation reaction is a reaction in which we can add the number of carbon atom. Here you can see that in the Getterman-Koch reaction, the pyrrole on reaction with hydrogen cyanide in acidic conditions with hydrogen chloride give us pyrrole 2 aldehyde. Here we are getting one more carbon in the product. We have introduced the carbon from the hydrogen cyanide. It can also further oxidized to give us the pyrrole 2 carboxylic acid. Then comes the Riemer-Tiemer reaction. It is also a formulation reaction. Riemer-Tiemer reaction you might have learnt in the phenols. Phenol when react with chloroform and in the basic medium and with the KOH, it also gives us the salicylaldehyde. That one aldehydic group has been introduced in the phenol. Here also in case of pyrrole, when lithium salt of pyrrole is heated with the chloroform in the presence of potassium hydroxide, we will get pyrrole 2 aldehyde. In addition to this product, we are getting 3-chloropyridine. What is it? It is a ring expansion product. In case of Riemer-Tiemer reaction, ring expansion also takes place. through the attack of dichlorocarbene. This dichlorocarbene is a reaction intermediate. It is a neutral intermediate. We can see from the mechanism of the Reamer-Timmer reaction. After the attack of this is the dichlorocarbene, it will attack on the pyrrole nucleus. After the attack of this dichlorocarbene, we will get a transition state, that is a bicyclic intermediate. It can go via two ways. In the first way, if this intermediate, after the species formed by attack of dichlorocarbene, first it will undergo protonation followed by hydrolysis. It will give us the pyrrole 2-aldehyde. But if it will undergo bicyclic intermediate formation, here you can see the two cyclic compounds are here. One cycle is of pyrrole nucleus and one is from the dichlorocarbene. This is a transition state. Since these chloride ions are highly electronegative, it will take the electron pair with them, and this bond, this carbon-carbon bond will expand the ring to make this 5-membered pyrrole ring into a 6-membered pyridine ring. So here from this reaction we are getting the 3-chloropyridine. This is very important reaction to increase the number of ring size. Then comes the Kolb-Schmidt's carboxylation reaction. Pyrrole reacts with aqueous potassium carbonate heated at 100 degrees centigrade will give us the pyrrole 2-carboxylic acid. Here also the carboxylation takes place at the position number 2. Then comes the coupling reaction. Pyrrole undergoes coupling reaction. It forms many dyes. Pyrroles couples with aryl diazonium chloride in a weakly acidic solution to give again 2 substituted product, that is the 2-aryl azopyrrole. This is a coupling product, this is a dye. If we take this diazonium chloride, benzene diazonium chloride in the acidic medium, then we will get the 2-phenyl azopyrrole as a coupling product. These were the electrophilic substitution reactions. Pyrrole further undergoes reduction and oxidation reactions also. In case of reduction, pyrrole reduces via 2 ways. We can do the catalytic reduction also and we can do the simple reduction also. In case of simple reduction, first we will get the pyrroline product in which only one of the double bond has been reduced by a zinc and acetic acid. Then further reduction with the help of red phosphorus and hydrogen iodide will give us the pyrrolidine, which is completely reduced product, which is a completely hydrogenated product where both of the bonds have been hydrogenated by the hydrogen atoms. Pyrrole can also undergo catalytic reduction by the catalyst nickel and hydrogen at 200 degrees centigrade. We will get here the pyrrolidine. Pyrrole is oxidized by chromium trioxide in acidic medium to give us the melamide product. Here also the oxidation will take place at the position number 2 and 5. In addition to all these reactions, pyrrole undergoes some specific reactions also. One of them is the Mannich reaction. Pyrrole undergoes condensation reactions. Here pyrrole condenses with the molecule formaldehyde and a secondary amine to give 2,N,N dimethyl. This is 2,N,N dimethyl aminomethyl pyrrole. How this Mannich reaction takes place, how this condenses? First of all, this formaldehyde and this secondary amine, they will react together to form a Mannich base. Then this Mannich base will condenses with the pyrrole molecule and will give us the product, that is the 2,N,N dimethyl aminomethyl pyrrole. Pyrrole also reacts with the maleic anhydride, although all these anhydride groups on these adds on the conjugated dienes and they give us the addition products. But pyrrole doesn't give us the addition product. It adds malic anhydride in a different manner in a Michael type addition, where this malic anhydride acts as an electrophile and pyrrole itself acts as a nucleophile at position number 2, and there is a electrophilic nucleophilic reaction and at position number 2 of the pyrrole, and this malic anhydride condenses here, which after hydrolysis will give us the 2-pyrryl succinic acid. Before this dehydration, it forms the 2-pyrryl succinic anhydride, and all anhydrides after hydrolysis give us the acids, diacids. Then comes the Hofmann's exhaustive methylation. This Hofmann's exhaustive methylation is a very important reaction in the preparations of alkaloids. Here the pyrrole ring can be opened up by the application of this methylation mechanism, in which first of the pyrrole has been reduced with the help of sodium ethanol or by the platinum hydrogen. First these two bond pairs have been reduced to give us the pyrrolidine molecule. This pyrrolidine then will undergo alkylation followed by the reaction with silver hydroxide to give us the hydroxide salt, which on heating will reduce 2 molecule of hydrogen, 2 molecule of water, and will give us the N-dimethylamino 3-butene. Here you can see that the ring has been opened from one side, from this carbon nitrogen side. This position has been opened by these 3 steps, by alkylation, by this hydroxide reaction, and by heating. Now for the opening of the second site, second carbon nitrogen bond, we have to repeat these 3 steps again. Here we have repeated in the same step. This alkylation has been done, this reaction with the silver hydroxide, and then heating. And here you can see that this nitrogen carbon bond has been opened, and here you will get this 4 carbon butadiene, that is 1,3-butadiene, and the dimethylamine, and water is also eliminated. Pyrrole also shows ring opening reactions with the help of hydroxylamine in the hot ethanolic medium. When pyrrole is treated with the hot ethanol, the ring of the pyrrole has been opened to form the dioxime of succinidialdehyde. So this is the succinic acid part. This is the succinic acid part where we are having the 4 carbons. This is the succinidialdehyde, this half, which will form these 2 oxime parts. It is from the pyrrole molecule only. In the pyrrole molecule, we are having this half part 4 carbons, from where we will get succinidialdehyde, which will form oxime with hydroxylamine, and we will get here the dialdoxime. Pyrrole also condenses with aldehyde molecules. Pyrrole undergoes condensation with aldehydes at alpha positions to give us the dipyrryl methanes. Here we have to take the 2 molecules of pyrrole. 2 molecules of pyrrole will condense with the formaldehyde at the position alpha, and these are the 2 pyrrole molecules, and this carbon has been introduced from the aldehyde, so it will give us the condensation product, that is a dipyrryl methane. These dipyrryl methanes are further used for the synthesis of porphyrins in the natural pigments. Porphyrins are the rings where we are having the 4 units of pyrrole nucleus. So these were the main reactions of the pyrrole compound, of the pyrrolidine compound. Now I want to summarize the lecture. So pyrrole is a aromatic heterocyclic compounds. That's why it doesn't undergo addition reactions of conjugated dienes. It shows the reactions of a aromatic compound, basically the electrophilic substitution reactions. Since it is having a lone pair on the nitrogen, so it is a weak acid also and a weak base also. It reacts with acid also. It undergoes electrophilic substitution reactions like halogenation, nitration, sulfonation, acetylation. It can also show acylation reaction. We can add carbon to the pyrrole by the formulation reaction and by ring opening reactions can be done. It can undergo ring expansion, and by the ring opening mechanism, it can undergo reactions with the manic base, with the aldehydes, etc. It shows condensation reactions. Now here are few questions whose answers has been answered in the lecture. How is pyrrole synthesized? What happens when pyrrole is treated with chloroform and boiling alkali? Next question is, although pyrrole is basic in nature, it does not form salt with strong acids. Why? How pyrrole is more reactive than pyridine towards electrophilic substitution reactions? Pyrrole has two double bonds, but it doesn't behave as unsaturated compound. How you will justify it? Why does pyrrole behave as a very weak base? Discuss the orbital structure of pyrrole and what is the state of nitrogen in the pyrrole molecule. If the electrophilic substitution in pyrrole occurs at position number 2 or position number alpha, not at position number 3, justify. Out of pyrrole and pyridine, which is more basic and why? Explain why pyrrole is weakly acidic than phenols. How will you synthesize pyrrole 2-aldehyde from pyrrole? Give the mechanisms of some electrophilic substitution reactions like nitration in pyrrole. And what happens when pyrrole is treated with following reagents as nitric acid in acetic anhydride, sulfur trioxide in pyridine, benzene diazonium chloride, bromine in alcohol. Next question is, how will you synthesize 2-phenylazopyrrole from pyrrole and what happens when pyrrole is reduced? So these are the simple questions whose answers can be explained on the basis of the reactions explained by the pyrrole nucleus. Thanks.
With this note, thank you ma'am, thank you so very much. And dear friends, we have given an exercise for you over here, and we would like you to answer the questions, as well as if you want your answers to be checked, then you can mail the entire answers to us at info.cc@nic.in, and of course we will try that Dr. Sushila Singhal herself check the questions and give the answers of the questions in the next session when she visits our studio. Till then, we say goodbye to you. Write to us at info.cc@nic.in. We would be meeting again soon. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.
Thanks.